about, right? People just come and ask questions.
Yeah, basically.
Okay.
It's not high at all.
So this right here for A, I know that if you draw low diagrams, the forces point up and to the right, so overall the results will be like that angle. So for my part A, I only did the magnitude. So I'm also supposed to like factor in the little angle here too, right?
Yes, I suppose you need to find an angle between them, or just find the x component and the y component of each one. You also accept that answer usually.
Also, right now I have like the x and y resultant, right? That combine together.
Right now you have.
Because I just did a squared plus b squared equals c squared.
I1.
Basically like that. Doesn't make sense. So
see, yeah, that's. At 6.8 degrees, okay.
right, yeah.
So yeah, I guess if you want, I mean, you have to specify. If it's a vector, you always specify it with the direction and the magnitude. Or you can just get its two components. That also tells you something about magnitude. So if you just did this,
so I just missed the angle.
This is x. Yeah,
makes sense.
Just missed the angle. It's
at
6.8 degrees.
Okay.
So that's where you lost.
And then I didn't look over what for B yet actually.
Calculate force on 2 meters of I3
to I1. So I3 to I1. So then we just disregard that wire. So I just put the wrong 0.04. 0.04 is the distance, right?
Force on I3 only due to y1.
No, so
This is on I3 due to y1 at 2 once. So the distance is, the question says,
4 centimeters distance.
Okay, 1 centimeters, 4 centimeters, right?
And that's why it's
Wait,
0.04.
Yeah.
Okay.
So it's 0.04. What do you have here?
I got √6 or something like that. I don't know why I did.
Maybe you did that.
Maybe, yeah.
You did this, yeah, 2 into √8. Okay. Yeah, that's just 0.4. You just messed up which two wires you're calculating on.
Okay.
Now, you actually did I1 and I3 also, so I don't know why that happened. So, I mean, you knew which two wires you were taking into consideration when you took her out of distance.
I just messed up.
Yeah, that's fine. Those are.
Okay.
Also, you also don't have a direction. Remember, vectors always put directions because you lose points on that. I mean, if it's a vector, you have to put magnitude and direction. I mean, if it's on the x-axis, you can just simply say to the right, or just draw an arrow going that way.
Okay.
It's really not a question. There's a point over that, yeah.
And then we mentioned this briefly in class, but I'm not sure what the closed interval means. Doesn't I thought it was just 0, so it's closed means you go from like your starting point and then you end the same place.
This is B.dl. This is Ampere's law, right?
Yes.
Okay, so Ampere's law. That's actually part of Ampere's law. Formula sheet here. I don't want to use stupid wrong formulas. I believe that's closed.
Should I try and get it from the sheet?
No, it should be right because you get this from that, and it's 2 pi r. So if you have L equals 2 pi r, which is the parameter. I mean, circumference of the circle. Sorry, it's 2 pi r. That's your L here. That's constant. That's how we got these. But anyway, this is Ampere's law. This is a statement of Ampere's law. It's one of the basic laws of magnetism. So you actually derive these from that. Okay. Right? You can actually see that. If you remember how we did Gauss's law, how we derived that, how we derived the other laws from Gauss's law? Because so when you have a wire and you take a magnetic field here, the magnetic field is going to be pointing here, and your dl is also going to be that direction. so we go in the same direction. So the dot product gives you b times L for this cosine 0 when when two vectors in the same direction, the dot product, and then it's just the regular product, right?
Yeah.
And so your dl, so that's just b dl, and since b is uniform throughout the entire surface, b dl just gives you bl because it's a constant.
Right. It pops out.
Yeah. So bl is equal to mu naught I enclosed ul is the length of the entire path, which is the circumference 2 pi r divided by 2 pi r. You get that equation. But anyway, that's amperes. So amperes law. This is how it tells you. And I remember you did one of these in the class.
Yeah, I'm sure we did. Like,
Well, like something like that. Yeah, you have basically you have a current page, and let's just do one wire for now, I guess. And you have a path that goes from here to here, for example, right? And or an entire path. So if you want to see enclosed path or the path from A to B, for example. Right? So, I mean, without even calculating the integral, you could say anywhere b dot dl along a closed path is always mu naught times the current enclosed in that path. So if you take this path, what's b dot dl? The integral of b dot dl along this closed path. This path. This is the path that we're moving. This is your L. So that's your small L. Here's small L. Here's small L. Here. You're summing up all these L's dotted with b.
It'll still just be your current.
It's always going to be mu naught times the current that's enclosed inside that path. So if you have a wire here, that doesn't take it into effect because it's not outside. Yeah. So here, he wants what is the closed path integral taking from point P
to R. And then continue the circle back to P.
Okay. P to R and then continuing back. That's but yeah, B to R and then back all the way to B. So that's you take B and then you go to R and then you continue along that circle, same diameter, back to P. So that's an enclosed one. So that's why you have that circle around the integral. So that would be just mu naught.
So I just do some Pierce law.
Yeah, it's just mu naught times I enclosed. So I enclosed would be, since they're in opposite directions, it's going to be the arithmetic sum of them. Right, so this minus the other? Yeah, no, not absolutely. So if the current, so if this had another current going in that direction, I2.
Do you have sum them up, right?
Yeah, you sum them up and see which one is bigger. And also depends, so the integral is either positive or negative depending on how you're going. So here he said you're going P to R and then back to P. Oh yeah, I see why he worded it now. So P, let's call this P, to R, P to R, and back to P. Look at this integral. So this alone is B dot dl. That means if L is the direction of motion. L is the length of the path. So at this point, if you're going from P to R, dl is going to be pointing in that direction. That small segment is going to be pointing in that direction.
Isn't that a positive?
Yeah. So if B is in the same direction, the dot product is going to give you positive because this would be B dl cosine theta. If they're in the same direction, theta is 0. Cosine theta is 1. B dl is just B dot dl is just B times dl times 1. If they're in the opposite direction, so if your B comes out to be in that direction, B dot dl, the angle between them, would be equal to 180 degrees. That would be negative. Okay. So in this case, which field would be greater? As its axis aligned with the z-axis, it carries the inner from the starting current I. So I 5.6 is the total current distributed over it, right? So the total current 5.6 going outward, right? And 3.5 is going inwards. So the one that's outward is greater. So the magnet. So yeah. So 5.6 minus 3.5, right? Yeah. So that total current is going outward, and that means the magnetic field it produces is in that direction, counterclockwise. So it's in the same direction as the integral. I don't know how you do it. Which right hand rule would you prefer?
I mean, which right hand?
I mean, there's this and there's.
I do it like this. Okay.
Yeah. So yeah, current and the direction that your fingers spin. You do this, and that. The one he does? Or so how would you determine determine the direction of this? Of the magnetic field
point my thumb in the direction of the current.
Okay, yeah.
And then
Alright,
finger
so
scroll.
Finger scroll determines the magnetic field. Yeah. So yeah, the total is outward. That's the bigger one. So your fingers will curl in the counterclockwise direction.
Because of that.
That means B points upward, right?
Yeah.
And since your L also points upward, because he said you're going from P to R, then back to P again, P to R, so both are in the same direction. That means your integral would be positive.
Okay, cool. That's much more simple when you explained it.
So, and sometimes he would ask you from P to R. So in the pre-lectures, they ask you only, in the homework, they ask you only from P to R.
Right, and if you do it like up and then left.
You can do that, yeah, but I mean, no, it's simpler to go throughout the entire, through the radius of the.
Oh, yeah.
Because when you're going, I mean, not the radius, the circumference of the circle. Because when you're going along that path, you know that the B is constant. So B here is the same as B here, but the direction is different. Magnitude of B here is the same as B here, B here, and B here. And B dot dl is going to be the same. Because when you're going, B is going to be in that direction, dl is also in that direction. Here, B is in that direction, dl is in that direction, etc., etc. So you can calculate the entire integral, and if that path you're taking is uniform, so the magnetic field along it is uniform, is the same along this path, you can just divide it by the length of the path. So the length of the entire circumference, so the portion of that path, so here, if you only want it from P to R, this is 45 degrees because you have 0.707707, right? So that's 45 degrees is 8 of the circle?
Yes.
Right? So you would take this integral over 8. So mu naught I equals over 8 would give you that. But that only works when the magnetic field is uniform throughout the entire path.
Makes sense. I think a couple of points off on seeing the voltage on the right side of the loop.
To the right, okay, infinity wire is this much outside the loop, okay. Which way does the current flow loop? The loop's clear across the left side of the loop, you've got that right. Okay, what are the voltage across the right side of the loop?
I thought on the right side you just add this distance here too, along with the length of the loop. But that wasn't it. EMF is equal to VLB. L is.
Why did you add this distance here?
Because you want to right side the loop, right? So you
Right.
add this distance.
For what? For which variable?
For L.
L is the length of the loop that's moving.
Only the length of the loop.
Yeah. So you kind of got the idea. Well, kind of. So remember the example in the pre-lectures? This is on a rail or something. You have this bar here.
Yeah, this bar is really confusing actually.
Are they?
Yeah.
Alright, let's try to walk you through this. So this is just a bar that's moving. This is like a conductor thing. Alright? And this is also a conductor. But this is only moving at a speed here. This is stationary. And this bar is moving. Right? So when this moves, it generates an EMF. So that's direction motion, P. If your B is going inward, you have the B that's going inside the page throughout this entire thing. So it's also here, everywhere around this moving bar. V, that's your B, and your EMF is going to be upward. So that's going to be the direction of EMF, right?
How do you find that again?
V. So which right hand rule do you do for these?
You use the equation QV cross B, right?
You can do that, yeah. So you can do that to think about them as. So it's the one for EMF that you used here. It's EMF is equal to VL cross B, right? This one is derived from QVB, right? This is the force, right?
Yeah.
So QVB. So how do you do just the right hand rule? So I can use the same one you do for QB cross B.
I believe.
You do this one, the curling, or do you do
curling?
The curling?
Right,
so
curling.
V, right?
Oh,
so when you have
the curl of the first part.
First V, curling inward, it's the second part. And this will point in the direction of force.
So curl like this, right?
Yeah. So V, this is V.
Right?
That's a force. That's a force on each point. This is the force on charge. That's a force on each charge inside this bar. Each positive charge inside this bar gets affected by a force that's upward. Right?
Yeah.
The positive charges go upward, and remember the negative charges. If the charges are negative, it's going to go the opposite, right? Remember when they asked you about an electron moving inside a field, and then they said a proton moving inside a field? Each one curved in the opposite direction, right?
I believe so, yeah.
Remember this in problems like these where you have this, and one would go like this.
I don't remember.
So if it's a proton, it goes the opposite way of the electron. Because you use the right hand rule only for positive charges.
And then it's like a negative charge.
Negative charge, you flip the right hand rule. So that's where the positive charges go. Negative charges going to go here. Positive side, negative side, that's going to create an EMF.
Okay.
That's your EMF that's created. And you can derive this from that. You can derive this, the EMF, from this. But we'll not derive it out. We'll just do this.
Actually, maybe it would be helpful to derive it because to show you that L is going to be maybe I'll derive it.
okay. So
B, okay, so I across B. I is not I across B. I'm not sure if you want, I can make sure I want to.
So what I just want to try to show you that this L is actually the length of the segment that's moving, and not the distance from anything. Because I mean, this also applies to this situation. This is L, the length of the bar. This is UL. This is UV that's coming out, and this is the V, the velocity it's moving at.
Right.
So it's just the length of the bar that's moving.
Okay.
So in this case, you'd have to put, this is your L, just like you used here. You actually use 0.08 for it, so you use it right here. Just length of the bar.
On the left side of the loop. So will it be the same?
No, it won't be the same just because the magnetic field isn't the same.
Oh, because it's further away from
It's further away from the wire.
Yeah.
So you have to see how much
So the B
magnetic
changes.
field is here. Yeah. So you need to see how much magnetic field is here.
Oh, so here the R that changes, right?
Right. This R changes.
That's when you add 0.1.
Right. That's what you add 12 plus 0.04 over the R. You can also do it the same way you did this, because these are just two wires. This wire and this wire. These are just two wires that have a mutual force between them, right? So same way you did this. Mu naught over 2 pi d, I3, I1 times R. So mu naught over 2 pi d, this is your d, right? This is one of your currents, this is your other current, and this is the length of the wire you're trying to find
Okay.
the force on.
That makes sense.
You see?
Yeah, I get it now.
You can do that too.
Small misconception. And then, what do you think you just want to find a current? So, because I found the incorrect voltage here, my answer here is also wrong, right?
So yeah, it's gonna be wrong, but I'm gonna see if you did everything else right. The resistance will
What would
be
you say the
0.8,
resistance?
basically V over R. Yeah.
Okay.
Oh, I'm not doing this.
Alright. Unless it's
I don't know. Usually it's when you build, you start doing something, and you make a small mistake here, you get an answer, you use that answer for everything else. If you just do the concepts right at that point, it should be.
oh wait.
Yeah.
And then right here, we have a little circuit. And we want the voltage across this resistor, the 3 ohms. So why is there?
Simplify it.
Alright, this simplifies. So R equivalent 7 over 3.
That's 4, 1, 2, that's 6. 6 and 1 to 2, that's 3, 6, that's 2, right? 2, 1, 4, that's 7. 8 over 7 is 1.14. And the voltage drop across the current 1.14. Okay, so the current so the 1.14 current is this current that's going here. Yeah, through the main loop. It's not the same current as flowing through this, because it's like some of the current goes here, and some of the current goes here.
So that's not really.
So remember when there's if this is your I0 here, there's a different current flowing through this one. This is going to be 1, this is going to be 2. These are not necessarily the same.
Right, because
Yeah. Some of it goes here, some of it goes here.
yeah, that is like that.
You could have done what you could have done instead of going through all this stuff. So
So what I do is like I work backwards from.
yeah,
you can work
backwards. But you can work backwards, and if you're smart about it, you can do shortcuts. So originally we had this circuit, and you can see it from here. Right. And then what you did is simplified this into 2 resistors. And then what you did is simplify this as 1 resistor. And then finally you ended up with
A series.
A series, right? Now, it's always useful to keep track of the nodes. This is a node. What does a node mean? A node is,
It's where they split, right? Currents.
yeah, you can think about it where it splits. A more general thing is that where the voltage is always the same. This entire thing, the voltage is the same because it's a wire, right?
Yeah.
So if you move from here to here, there's no voltage drop. From here to here, there's no voltage drop. Because you're only moving across a wire.
Wait, so even at this point, voltage is the same?
The voltage here is the same as voltage here, is the same as voltage here.
Oh, so it changes after it goes for
After it goes up through one of the resistors, it's changes. So it's always kind of helpful to keep track of the nodes. This node is the same as this node, right?
Yeah.
This is the only thing changing. Now when you combine them together, it's the same as this node. Yeah. But that's the same as this node. This node is the same as this node, because this resistor, right?
Yeah.
That's this resistor. The sum comes up to this resistor, right? So that's the same as this node. Now if you go back here, this node, same as this node, same as this node, right? Right?
Makes sense.
You see that?
I see it.
Right. This resistor is the same as this resistor, right? This one is the sum of these, and this node here is this node. Do you see that?
Yeah, I see it.
Sure? Right. So this node, and the difference between these two nodes is going to be the difference between these two nodes. So if he wants the voltage difference across a 3 ohm resistor, that's the same voltage difference across these two nodes, right?
Mm-hmm.
It's a 3 ohm resistor, because there's no change, there's no voltage drop across this entire line. Right? So that's the same voltage drop across here, across here, across here.
And it'll be easy to do it across.
Just I times the 2 resistor that you got.
Yeah.
And that's a voltage drop across that 3 ohm.
Okay. So I could do the same process for this resistor, right? 2 ohms.
You might have to expand a bit. So some nodes, when you simplify a circuit, some of the nodes are preserved. In this case, that's why I told you have to be smart about it, because it's not something that always works. Sometimes the nodes are preserved. These two nodes are still the same as two nodes, same as these two nodes, same as these two nodes. But in case of the 2 ohm resistor, you don't know where that node is. I mean, it was from here to here, so let's use from here to here. Here, it still existed. But when you combine these, you don't know where it is anymore.
So you
You know the bottom one, and you don't know the upper one where it is anymore. So you'd have to expand.
Okay. That's good. So I can just work on that later. And here are the Kirchhoff's rules. This is plus. And I started negative.
Mm-hmm.
Long direction of currents. Why is it wasn't it still a long direction?
You did this the other way around.
Did I?
So I mean, you get to choose which one. So where's your loop here? So let's do it here. Let's just do. So is that, I mean, which, sorry, I shouldn't assume you went that way. Which direction? You did? You did go there?
Yeah.
Okay, that's one, that's the other.
Mm-hmm.
Alright, so if you want to do it like you did, which I find easier to think of, when you're going across in the same direction as a current, it's a voltage drop. So that's negative I1 R as well as I1 R2. Negative I1 R1, right? And then another drop here. You did negative I2 R, no, sorry, negative I1 R2. R2. You're going in the same direction as the battery.
How would you look for the battery? I guess I forgot that part.
So
That part of it.
this is the positive and this is the negative. And the battery is trying to push current out of the positive direction. Because when you only have a battery and a resistor, you know that the current is going to go that way, but that's a positive and that's negative.
Yes.
So the battery is trying to push stuff that way.
Mm-hmm.
So in this case, there's a voltage gain across the battery.
Isn't that still going the same direction though?
What do you mean?
The current is going this direction.
Yeah, the current is going in that direction. But this one, so this is Kirchhoff's second law, rule, the voltage, one rated to voltage. It says that the changes in voltage is the same. So what you're saying right now is there's a voltage drop here, and a voltage drop here, and a voltage drop here. So there's a loss of energy here, and a loss of energy here, and a loss of energy here, without any gain. So that's negative energy. That's,
it has to be 0.
it has to be 0 because energy has to be conserved. So resistors will always lose energy. The energy lost across the resistor must be gained across the battery.
Okay, I get it.
Sometimes in the equation you might end up putting plus for a resistor just because you're assuming that current's going that way.
Right, that's good.
Right? So you assumed here that I1 is here. Actually, this should be I2, right? According to what you do.
I did I2.
I2, yeah. It should be I2. Condition analysis, that's it. I2. So you're assuming I2 is going downward. Are you assuming that?
Yes.
Okay. You're assuming I2 is going downward.
But
And
I
you're
was just going
assuming,
to, so.
and you're assuming this current's I4 is going that direction. Right? So
Right, so if you look at the battery and how do you do that? It's just 12 volts, that's it? Positive 12?
Yeah, positive 12 volts, because you're going the same direction as the battery. You're moving the same direction as the battery, right? Minus I1 R1, because you're going in the same direction as the current across the resistor. Minus I2 R2, because you're going in the same direction as the current across the resistor.
It's equal
It's equal to 0. The second equation, undo it through the battery. Minus or plus?
I'll be minus.
Minus, because you're going opposite. It's trying to push that way. You go in the opposite direction. That means it's minus. So minus, what is it?
8 volts.
8 volts. Minus 8 volts. We assume the current is going in that direction. And we're moving in that direction. So that's
Also minus.
minus I4 R3.
Yeah.
In this one, we assume the current is going in that direction. And we're moving in that
So
direction.
yeah.
Plus I whatever. I2 R2, I guess, is equal to 0.
And then the last equation, just like I1 equals
Yeah.
these two add together.
Yeah.
We use the algebra.
Yeah.
Which I don't have time.
You didn't have time for that?
You have to do it like with a matrix, right?
You can, yeah. You can do it in matrix
I did one time in the arc, and then I don't know what I did.
What?
I did one time in the arc. I showed you one time in the arc.
Wait, with the matrix, you mean? How did they?
Matrix, yeah.
With the calculator? Which calculator do you have? The TI?
TI-84.
Oh, I don't know how to use this.
You don't use it
No.
Which one do you use?
Do you know how to pull out the matrix one? Yeah. Like, yeah, I can show you how to put it in form, possibly. But no, I never use a TI. I have like a complicated calculator that's disguised as a scientific. It's a basic scientific one.
So here's this old problem that they did. That's fine, I could just do it in algebra.
See if the determinant of a matrix that I know is right. So, no, that's zero. Where's the menu? Where you go before the matrix? Because yeah, this is just here. You just select it from here.
Could be math. Like that, right?
Let's see solver.
That's not too important.
Okay.
I don't want to waste your time on that.
Sorry. Yeah, I don't know how to use these. I think I should learn. Alright, that's all.
And my final question is about the capacitors, because I didn't get that right too. Only got half of it.
What did you do? What's the current that passes through R1, right? Or switch the loads. You got that?
Yeah.
Okay. Which one did you get?
C and D.
C and D. C is what is the current R2 after the switch has been closed for a very long time. Switch is closed for a very long time. What happens to the capacitor?
Well, it's fully charged, and then it shorts.
Right. This thing.
Just
regardless,
regarded.
right? So what is the current through R2?
Do you do the voltage drop or no?
No, it's just current.
So
So
all I did was just do 12 volts over R2, which is 30.
but so when it short circuits, when it short circuits, that's your circuit basically. You have current flowing through that.
Right, you just ignore the middle part.
Right, you ignore the middle part. And you want the current that's here.
Mm-hmm. So I use the V equals IR.
V equals IR, right?
And the V is 12 volts.
We know the V is 12 volts, which is the voltage from here to here. It's 12 volts.
And then R's, well, this one's 30 ohms.
That's 30 ohms. But you don't know the voltage across here.
That's where I got it.
If you know the voltage across here, yes, you can do that. but this is a voltage across all 4 of them. But you know that the current is the same. The current through each one of them is the same.
The current reach was
Because they're in series.
right.
There's nowhere else that the current's going to go. You can't go off the wire. It has to keep on going through the wire.
So you find the total resistance first, you find the current,
Right?
and then
That's the same current.
You find the voltage.
No need. That's the same current. We
Oh,
just
that's
said
it?
they're on series.
And that's all you gotta do.
Yeah.
Okay.
They're all in series.
They're in series.
Yeah. Since they're all in series, the current through all of them is, the current through each and every one of them is the same as the current through all of them, which is the same as.
That makes sense. So then, I guess that's the same idea applies to part D when you open the switch.
Mhm.
That means you ignore this part after very long time, right?
Yep.
Okay. So also
Oh, right after the switch is open.
Yeah.
Yeah.
So you just ignore that part.
Right.
Okay. Also the same idea.
Same idea, but let me see what you did with the. What's the voltage of the capacitor though?
Isn't it 12? It's fully storage, just the voltage battery.
But there's a voltage drop across it. So at this point, this is, you should have a capacitor here. I'm going to draw it in. So this is where your capacitor should be. It's not really connected because there's no current flowing through it. It's like it's not connected. But the voltage from here to here across the capacitor is the same as the voltage from here to here, which is the same as the voltage here to here. So to find the voltage across the capacitor, it's not the same as the voltage of the battery because there's a voltage drop from when you jump. There's also a voltage drop when you jump.
So it's not a battery.
See what I'm talking about?
I guess see where it's going.
So that's a voltage of the battery right there. That's a voltage of the capacitor. It's going to be the same as the voltage drop across these 2 resistors, or it's going to be the voltage across the voltage of the battery minus the voltage drop of these 2 resistors.
Can you repeat that again?
Okay, so how would you find this voltage? DC. You can either do, let's call these R1, R2, R3, R4, and this is BP, or 12 volts, let's call it. Let's give it 12 volts, right? So, one DC, that's either. You can either look at it on the right side, it's the same as the voltage drop across here. So that's VR1 plus VR2. VR1 plus VR2, right?
Yes.
Or 12 volts minus VR4 minus VR3. Because you can either look at it from the right or you can look at it from the left. If it's from the right, it's a voltage drop across these.
Right. Seems more simple.
Yeah.
Yeah.
So you need the current for it. Or if you look at it, if you need to look at it from the left, I mean, it's just the battery, because you have a gain in the battery and a loss in each one, a gain in each one of these.
Okay. I get it now. Hopefully. Small details of it.
This is basically the application of Kirchhoff's law. So we find a voltage between 2 nodes. If you need to find a voltage between this node, simply 1. So you need to find the voltage between 2 nodes. You can use the same thing you do in Kirchhoff. When you use Kirchhoff's law, you go up, down, or whatever, and then back here. You know, it's 0, right? This is basically the other way. You don't know what it is, but you know the changes. You know the change from here to here, from here to here, and then from here to here. So what's the change across this one? It's going to be negative I R3. You found your R from your previous question.
That one?
Yeah, it's the same as R3, remember?
This one, right?
Oh, wait.
You just label them.
Yeah, before, at infinity, yeah. And this, because the voltage of the capacitor, so when the switch opens, the voltage of the capacitor right before the switch opens is the same as the voltage of the capacitor right after the switch opens. same, right? So if you find it before it opens, you're going to know it right after it opens.
Before it opens or right after it opens?
Yeah. At that moment when you're switching the switch, the voltage capacitor can't change. It can't jump. It doesn't jump instantaneously. It has to change. So you know right before the switch opens. And so if you have time graph, and this is where the switch is changed. If the voltage is changing like this, it can't jump and do something else. It has to be a smooth graph. It has to, the same voltage that's before has to be the same voltage after. So if you look at this point from the left, it has to be the same point from the right. That's the idea we always use. That's why we find it when we are asked about it right after the switch is open. That's why we go right before it's open and find it. And right before is infinity. Right before is to this question. What is it going to do a very long time? After it has been closed for a long time, but you're trying to find the voltage of it. And the voltage of it is voltage across here. And yeah, you find it with the current that you found before.
Okay. That's really helpful. Yeah, but that's all my questions for now.
How'd you do on the first exam?
110 out of 150. So it's slightly better than this one. So
Yeah, it's a bit harder.
Yeah.
This is a bit harder.
So we only have the final coming up, right?
Hmm?
We have the final for this class.
Yeah.
That's the last exam.
That's the only thing left.
So I guess I forgot. We came at beating this class. Do a lot of people do review sessions often?
Do what?
A lot of people come do review sessions.
Sometimes it varies. Of course, most attendance is always the day before the exam.